So just a reminder that we Lab 1 checkoff meeting, if you haven't done that already with a member of our staff, either a recitation instructor or one of our LAs, come by the staffed lab hours. It's just a short little conversation about your design for Lab 1, the CMOS gate. It doesn't take very long for the meeting. It can take longer for the wait. So we encourage you to come earlier in the week so that you don't have to meet up with everybody else who waited until the absolute last moment for a checkoff. We have a quiz Friday in section, so go to your assigned section, please, so that we don't run out of seats. It's tempting to everybody time shift to the 3 o'clock section, but there's only so many quizzes and so many sheets that will be there at 3 o'clock, so try to avoid us having a crisis at the last moment by going to the section where you actually do fit. To study for the quiz, we have a large number of old quizzes online. Remember that our quiz covers all the way through L5. In some terms, the first quiz only covers through L4. So if you're not seeing any questions about circuits with registers in them, in particular the timing about circuits with registers in them, looking at some of the old quizzes, take a look at some of the problems in the quiz 2s, because you'll want to be set for those too. You can be asking questions on Piazza. You can come to those staff lab hours. We'll be posting some quiz review videos where I'll work old quiz problems, and those will be posted by tomorrow. And we'll be doing a little bit of quiz review in section tomorrow. So, and just about everywhere you turn, there's a place to get your last-minute questions answered or practice. That doesn't mean you won't be nervous, but most things work better when you're a little nervous about them. So be nervous. That's good. You'll study harder and do better on the quiz. Any questions about the quiz? People who feel that they cannot make, for some reason, the Friday quiz, well, more than just, you don't feel like it, but if there's a good reason, then please email me by Wednesday to arrange to take the makeup. I believe I've responded to everybody who's emailed me about the makeup. So if you thought you requested a makeup and you didn't get an email from me, this would be a good time to say, oh, and then email me again. So today what we're going to talk about, and in fact for the next 3 or 4 lectures, is using our new register building block, our new toy, to build all sorts of interesting systems. And in some ways, the sort of rectangle and cloud schematic that you see sort of in cartoon form above the hack's head there, that's the hack and the nerd, but that's how I always think of them. So that's that cartoon is really a representative of pretty much all the circuits that we build in the digital world, which consists of storage elements which save state and computational elements that manipulate inputs and the current state to produce new states and outputs. And that's, that schematic diagram is sort of the key to all the digital circuits, and we're going to spend a little bit of time figuring out how to use it in an intelligent way. Before we dive into building finite state machines, which is our name for this sort of new abstraction that we're going to introduce, let me just remind you one last time about the timing involved in making register circuits work. So the canonical sort of setup is we have a register that's providing information to this combinational cloud, and then the result is captured in some downstream register. I've shown 2 registers here. If this guy looped back to the D input of the first register, everything would be exactly the same. The analysis would be the same. But basically we have a register sourcing information, combinational cloud, and a register syncing information. And this diagram down below is a fairly careful drafting of when signals are changing and when they're the same. So the clock edge, as you can see, is just in this case I've drawn a square wave. It's the rising edge of the clock, which is the so-called active edge. That's the one that loads new states into the registers. After the rising edge of the clock, it takes a certain amount of time for the output of the register to get contaminated. At least for a little while, it's maintaining the previous state value. After the contamination delay, you can't rely on the output of the register, so that's what that little hashed lozenge means. Gotta practice my words before I come down. And then finally, the output of the register becomes stable in its new state. So we're basically contamination delay, propagation delay. This funny symbol, this sort of graph here, indicates that the value is either 0 or 1. We're not being specific about whether it's 0 or 1, but we're indicating its periods of stability and when it changes. So when you see a clear lozenge, that's when it's stable. In other words, no changes happening there. And the hashing represents regions of time in which the signal may be changing. So that sort of sets up the timing for the values on the Q1 wire relative to the clock. We can then look at the output of the piece of combinational logic, which is also the input to the downstream register. And if we then take into account the contamination delay of the combinational logic, we can see that the star signal sticks around from the rising edge of the clock for the sum of the contamination delays of the upstream register and the contamination delay of the combinational logic cloud. In other words, this signal stays valid for a certain amount of time after the rising edge of the clock. It then starts to change and finally gets its new stable value after the sum of the propagation delays. It's this node down here, the star node, the input to the downstream register, where we have to then check that we meet the timing constraints imposed by the dynamic discipline. In other words, we have to meet the setup and hold times of the downstream register, and those are with respect to the rising edge of the clock, so that the downstream register will in fact work correctly. If we violate the setup and hold times, the downstream register isn't reliable, and in fact may do very funny things, and the very funny things are the subject of Thursday's comedy lecture, I guess. Okay, so this is a very careful diagram, and from this we'll get two timing constraints. And this is where you want to go borrow Professor Umbridge's pen. Remember the one that when you write, it inscribes in the back of your hand? This is a good thing to inscribe on the back of your hand. I mean, if you had to put down one set of timing equations, this would be the thing you should remember. And so while you're all cringing slightly, you can instead just say, how about if I just commit them to memory? And so the first constraint here, which is represented by this T1 interval, is the sum of the contamination delays. And that's how long the star signal remains valid after the rising edge of the clock. And we know that for the downstream register to work correctly, that the sum of the contamination delays has to be bigger than the hold time. Okay, so in rhythm, we all want to say the sum of the contamination delays has to be bigger than the hold time of the downstream register. So if we violate that constraint, the downstream register will not work correctly. So we have to somehow design our logic so that's true. The second timing constraint has to do with this T2 timing interval, which is sort of how long after the rising edge of the clock is it before we have a new stable value on the star signal, the one that will become loaded, that will be loaded into the downstream register on the rising edge of the next clock, on that rising edge. And the answer is, well, we're going to sum up all the propagation delays. The propagation delay of the register, that's here, okay, plus the propagation delay of the logic. That tells us how long it is before that star signal becomes stable with its new value, the one that reflects the new information coming out of the upstream register. At that point, the signal has to be valid for T setup. In other words, we have to meet the setup time of the downstream register. So what has to fit in between two clock edges? The propagation delay of the register, the propagation delay of the combinational logic, and the setup time that we need for this to work correctly. Okay. So these are the two timing constraints. They're not very hard to remember, particularly that we have umpteen practice problems for you to try it on, so I encourage you to do that. So how much time? So in some sense, the useful work is being performed by the combinational logic. How much time is there? Well, we take the clock period and we subtract off the propagation delay of the upstream register and the setup time of the downstream register. Those are properties inherent to the register, and we have to obey them, otherwise the registers don't work. Okay, I mean the downstream registers certainly needs its setup time, and the propagation time of the upstream register is just whatever the manufacturer sold you. So the clock period minus the prop time of the upstream register and the setup time of the downstream register, taken together, you subtract that from the clock period, and that's how much time you have in the middle to do actual work. This particular constraint down here, the sum of the contamination delays, might be handy if we actually design registers so that it was always true that their own internal contamination delay was greater than their hold time. That way, no matter if I, for instance, had no combinational logic and simply connected the wire, and you say, why would I do that? And you'll see when we do pipelining diagrams in the coming weeks that there will be times when we have so-called back-to-back registers. If we have this constraint here, if we actually design the register for this true, timing constraint 1 is actually met trivially. And then there are some issues about what happens when the clock signal doesn't actually get to all the registers at the same time. And that's called clock skew, and there's a nice tutorial problem at the beginning of the sequential logic tutorial which explores how the timing specs change. So you look at these two timing specs, okay, and one of them is a killer that keeps you up at night if you're an integrated circuit designer, and the other one has to be true, but you can always save your bacon after the fact. So which one is the one that after you've built your circuit, if it doesn't work, you just basically have to build a new circuit? Well, what things do you have control over? Well, typically you have control over the clock period. In other words, that's an externally supplied signal when you buy a processor. And in fact, Intel happily sells you processors that run at 2.5 gigahertz and 2.9 gigahertz and 3.1 gigahertz. What they've done is they've actually chosen from their manufacturing line chips that work better and sell them to you for more money with a higher clock rate. What they've done is that they've been carefully testing the circuits to see what their actual propagation delays are. And then they pick a clock period that makes the second timing constraint true. In other words, simply by changing the period of this external clock, I can make the second timing constraint true. Right? Because it is, the hardware will have whatever delays it has, so the setup time and the propagation times, that's what the hardware will have. But whatever it is, you can make clock period big enough that everything that has to happen between rising clock edges does. But what about the first timing constraint, the contamination delays? Well, if you don't have enough contamination delay, then in fact what will happen is the circuit will not work correctly, and there's no clock signal involved in that first timing constraint, right? I mean, if that is broken, you basically have to redesign your circuit to provide sufficient hold time. Right, so this is where computer-aided design tools come in. People spend as much time verifying the circuits these days, in particular things like these timing constraints, as they do designing them, and in fact, sort of a sad truism of hardware design that most of your time you're checking to see if you got it right. That getting it right part is fun. Checking to see that it is actually right is somewhat tedious because you have to check a zillion cases. You have to check this is true for every pair of registers that are connected by paths in the circuit. So it's quite, if you have millions of bits of register in your circuit, that's a lot of checking. So the contamination delay constraint, you have to get right in your circuit design, otherwise you have to redesign the circuit. The second constraint, your boss is upset if it's a 2.1 gigahertz processor instead of a 2.5 gigahertz processor, but you can say, look, the good news, at least I can make it a processor. I don't have to throw it away and say, gosh, sorry, maybe next year we'll have a processor. Okay. So here's our new machine. Okay, this idea of a state register and a combinational logic cloud. We have a notion of a current state that comes out, k bits of some, k seems to be our little index we often use to count the number of state bits. The combinational logic, in combination with the input bits, produces a new state and some output bits. So remember, the combinational logic is an acyclic graph that obeys a static discipline, and we can describe it completely with a truth table. Right? And since it has k plus m inputs, the truth table has to account for all possible combinations of those k plus m bits. So the truth table will have 2 to the k plus m rows. So all possible combinations of the k state bits and the m input bits. The engineered cycle is the only place, so this, even though it looks like a cycle, remember there's no pass-through path here. There's no combinational path from the D to the Q. In fact, we carefully built this clever little double gate mechanism to make sure there is no combinational path. There is no cycle in here. The engineered cycles that's referred to is in fact the positive feedback loop inside the latches. We've spent a lot of time, or as an engineer you would have spent a lot of time guaranteeing that little cyclic circuit actually works correctly, and transitioning from pass-through mode to storage mode, lenient muxes and careful timing and the setup and hold time. That's what all that's about. The engineering has gone in to make those cycles reliable for us. Okay, and remember, setup and hold time. Whenever you see a register, the first thing you should think of is setup and hold times, setup and hold times. Then you look at the hand that has that little inscription on it that you did. You know, there are times when Harry Potter sort of had it right. Okay, and so there's k state bits, so that can represent one of 2 to the k possible combinations of those state bits. Each one can be 0 or 1. We do have to respect the timing assumptions. And so typically the timing problems that you see look a lot like this one, right? Where we give you a bunch of numbers, often one of them has a question mark. And using those 2 timing equations, we can figure out the value for the question mark. Yes?
One register just keeps track of 1 bit, right? So if you want k bits, you're going to need a bunch of...
You need k of those individual 1-bit registers. We often draw them as a single box and just somehow indicate that there's k bits coming in and k bits going out. And you should just know that that's k copies of the single D register that we've been talking about. So we can sort of have a sort of a sloppy notation, but it tends not to be ambiguous. You just have to look at the number of bits that are being stored there. And you say, oh, I need as many individual register bits as the bits I'm trying to remember. So in this particular case, let's answer this question. The constraints on TCD for the logic? Well, we do have this problem of we need the sum of the contamination delays, so 1 plus question mark has to be bigger than the hold time, which is 2. So 1 plus question mark has to be greater than or equal to 2, suggests that the question mark has to be at least greater than 1. The minimum clock period, well, the propagation delay of the register plus the propagation delay of the combinational logic plus the setup time all has to fit in 1 clock cycle. So in this case it's 3 plus 5, which is 8, plus the setup time, which is 2, which is 10. And so we need a clock period a minimum clock period of 10 for this circuit to work correctly. If I run it at 9, the circuit will be flaky. And if any of you try overclocking at home, often what happens is when you're making your processor go faster and faster, making the clock faster and faster and faster, at some point you end up violating this particular timing constraint, and now the circuit is no longer performing correctly and your operating system crashes, and you say, well, maybe it's actually not a 5 gigahertz processor, and you turn it back, down your clock a little bit. The setup and hold times for the inputs you've gone over in lecture. There's lots of examples to look at. Okay. So that's sort of the mechanics of the building blocks. Let's think a little bit about how to build something using these building blocks. So we're going to start with a very simple example. We have a more interesting one towards the end of lecture. So what I want to build is a combination lock. So this is a synchronous circuit. It has a clock. And the idea is that I'm going to put a new input. The in is a single bit, 0 or 1. And I'm going to feed this circuit with a sequence of inputs. And what I would like to do is, and then every time I put a new value on the input signal, I'm going to make the clock have a rising edge so that it can consume that new input and then figure out whether I've entered the correct combination. And we would like our clock to open, to assert the unlock signal, that's the output. So we want U to be 1 if the last 4 values of in that I've clocked into the circuit are 0, 1, 1, 0. And just so that we completely connect the dots here, this is a sequence of inputs we'd like our circuit to process. We can't do that with combinational logic, where the output is always a function of the current inputs. Since we want to process a sequence of inputs, we'll need sequential logic, and sequential logic always involves these state elements which get clocked. Everybody sort of happy with that? So that's the basic strategy. We're going to spend a moment now designing the inside of that circuit. So we're going to introduce a new abstraction to help us think about that. Okay, and this is a very handy abstraction. Whenever I go out in the outside world to design circuits for people, you often will find me surrounded by napkins and engineering notebooks full of the diagrams I'm about to show you, because this is how you actually design sequential circuits. Okay, so again, the numerology is I have a certain number of states in my finite state machine. I have a certain number of inputs m and outputs n. And then I'm going to show you these two rules. Okay, so a finite state machine, basically, you have states, and then something happens, and you go to a new state, or to the next state. And the next state may be the state you were in, but it could be a different state. And so what we're going to do is build ourselves a little roadmap of how we get from state to state to state. Sort of like, you know, Google Maps, except it's for state machines. It shows us how we're going to transition among the 2 to the k possible states of the state machine. Okay, so we're going to design our lock. And so here's our first state. Now, all the states, well, typically when you design a state machine, they have a meaning associated with each state. There's a little piece that you can say, I know it to be, for my machine to be in this state. In other words, what's the value in the state registers, those k bits of state registers, the encoded value would tell me I'm in a particular state, and I associate some semantics with that state. So in my lock, the first starting state is a state I've not seen any combination at all. Right, so I've given my, I've used S for state and then X to sort of say I haven't seen any combination. So I'm trying to give my little state a name. For each state I'm going to indicate what the output I want to, in this case the unlock line, what output I would like associated with that state. And in this case, because we haven't seen any combination, we sure don't want to be unlocking the lock. And then finally, we identify one of the states as the starting state. So we have to design the hardware for this to be true, but at this level of abstraction, we want to identify conceptually where's the start of our journey through all the states. Okay, so we indicate that by a heavy line. Now, when we think about the combination, remember there's, in a sense, a 4-long sequence that we want to remember. And that suggests that what we're going to need, okay, is a set of states that represent successive bits of the combination arriving. So we have the state that we get to after knowing nothing is if the user types in a 0, we will say, oh, that's great. That's actually the first digit of the combination. So I want to remember that I've seen the first digit. So this state, S0, is distinguished from the first state in that this represents having seen the first digit of the combination. And in fact, notice that we've marked the transition, the little map we're making now, that goes from the initial state to this first state, second state, into the next state here. And we've basically said you can go from here to here if the input was a 0. So we're sort of marking down the conditions under which you make a transition from the initial state into S0. And similarly, we're going to have the other states that we need that represent the 4 digits. So 0, 1, 1, 0. So if those were the digits I typed in a row, and each time after I put in the new digit, I made a rising edge of the clock, I would hope that I'm designing my machine to go through this sequence of states. And when it gets to this last state, notice that this state represents having seen the 4 bits of the combination, I'm going to say, aha, this is when I do the unlock. But I sort of get, so this is sort of like, okay, I've tried to organize my thinking about the exact sequence of events, and I have a state that represents every step along that sequence. Well, you can ask yourself, you can say, okay, I think I get this. I can see how this machine, that if I typed in exactly those bits and then did a rising clock edge after each new bit, how I would make a journey from the initial state down to a state where the unlock signal would be asserted. But what happens if after typing a 0, I don't type the correct thing? I type another 0. So what we're going to do is we're going to handle all the other transitions in the diagram. So for example, if I just come in and start typing 1s, which is no part of the combination, even though I've seen some bits, I haven't seen the first digit of the combination yet. Okay, so there's this notion of staying in a state when you haven't seen the condition that you need to get to the next state in the sequence. And so forth and so on. Now some of these arrows may confuse you a little bit. So for example, why is it after I've typed in a 0 and a 1, which puts me in this state here, why is it when I see a 0 I just don't go back to the beginning? You can sort of say to yourself, okay, so 0, 1, that's good. 0 is not the correct next digit, so I should, I'm going to go, shouldn't I just go back, start over? Instead, I've chosen to go back in this state. And the question is why? Yeah?
That state represents you've seen 1,
Right. So this is clearly a mistake here. So what you're saying is that this is actually... giving away all my plot twists. Okay. So I've typed in 0 and 1. What I've done is I've typed in another 0, and that's not correct. So we know we're not there. But if the person goes ahead and types this, they're expecting this to work. Right? So what I have to do is to make sure that every time I see a new digit, I think of myself, I can say, well, that's not correct for the combination I was processing, but it may be the prefix of another combination somebody's trying to enter. So I make the arrows in my diagram sort of reflect that. I wonder what all the shocked look were. I just typed 010 on the board. It didn't seem that exotic. Okay. So here we have this new specification, this diagram. And it turns out there's a fairly systematic way to convert this diagram. Now that you've thought about this, it's easy to design, I think, state machines using this sort of arc and circled, circles for the state, arcs for the transitions. You can sort of understand what's happening at this level. And now I'm going to translate it into a truth table by keeping track of what the current state is and the current input, and then indicate what the next state is and what the unlock bit is. So what I've done is each of these rows here corresponds to, for every arc in this diagram, there is a row in this truth table. And what I've done is I've said the current state is where the arc is coming from, the next state is where the arc is going to, and then this unlock line is really just a function of the current state. It doesn't depend on the input. But I can put it all in the same truth table. You say, well, this is great, Chris. The trouble, of course, is that that's a symbolic name for a state. So instead, what I'm going to have to do is come up with a numeric encoding for my state names to turn this into an actual diagram, an actual truth table, from which I can now, how to design combinational logic using a read-only memory, or using a sum of products implementation, or any Carnot maps, any one of a number of ways. This is arbitrary. But it turns out that if you're careful about how you do this data assignment, sometimes your logic is a lot less. Because some of these truth tables turn out to be, trivially implemented, and others require lots and lots of gates. Right? And so if you're actually pretty good at the state assignments, you can usually make your logic, the actual logic you have to build to implement the state machine, smaller. Okay. So are we all happy here? State diagram. We'll go through some more diagrams of building a state machine in a moment. That'll be fun. But meanwhile, just the mechanics of it, we have this diagram. We have a way of turning this into a truth table. And now we're really pretty much all set to actually design the circuit that implements this finite state machine. The FSM is really just our abstract way of thinking about what we wanted the state machine to do. Here are two different types of diagrams. The one on the left is for what we call a Moore machine. The one on the right is a Mealy machine. And I have to tell you that the distinction is not hugely important, but they do have names, so I thought I would mention them. Here, the output bit, the output from the state machine, in our case the U bit, is associated with a state. Here it's associated with a state and a transition, so it is with a particular arc. And so those are, you can think of this in terms of the combinational cloud. You can think of the output being a function only of the current state or of the current state and the new input that's coming in. So it's not a big deal, but what is a bigger deal is thinking about what makes a correct state transition diagram. The first thing we should notice is that for any particular state, let's pick S2 here, I have to have, none of the arcs can have overlapping labels. Right? So in this case, we only have a single input. So that means that I would expect to find one arc labeled 0, corresponding to a 0 on that input, and one arc labeled 1. If I saw two arcs labeled 0, what would that mean? I think that's a great answer. We wouldn't, the statement, we haven't really been very specific enough, which transition does the state machine supposed to take? So that's a no-no, right? You can't, the arcs all have to be mutually exclusive. It's pretty trivial on a diagram like this, where we have one input and just two labels for the arcs. It gets more complicated when you have a lot of inputs, and you have to make sure that none of the logic equations that you've written about, the logic function of all the inputs that determines whether that transition is the valid one or not, you have to make sure that they are all mutually exclusive. The second requirement is not only are you not allowed to have two places to go for any particular set of inputs in current state, you have to have at least one place to go. In other words, you have to collectively exhaust all the possibilities. So there can never be a combination of inputs in a current state where the state machine doesn't know what to do. You have to really figure out all the things for this logic to make sense. So that's it makes sense. It's easy to design machines where you forget to do it once in a while. Typically, the arc people forget is the arc when you stay in the same state. Right? They forget to say, and if none of my output arcs is true, but I want to stay where I am, well, that should be represented by an arc back to the current state and the appropriate equation for when you take that transition, because that information will also have to be reflected in the logic. Because remember, that next state calculation has to be accurate, even if it's producing the same answer that it produced for the previous state. If you leave that equation out of your logic won't do what you think. So you really need all those loop-back arcs as well as all the arcs from transition to transition. So here's our hardware. And this is, what I've done is replace the combinational cloud by our general-purpose combinational logic device, the read-only memory, which takes in the current state and the inputs. In this case, there's 1 bit of input and 3 bits of state. Why 3 bits of state? Where did that come from? Whoa! 3 landed from the heavens. Why 3? Why not 2? Why not 7? Yes?
Because you need 3 bits to represent however many states you have.
So how many states did we have in the diagram? We had 5 states. How many different combinations can I represent in 2 bits? 4 combinations. Well, I have to distinguish among 5 different cases, 5 different states that I could be in. So 2 bits isn't going to do it. 3 does, right? So that's where that 3 came from. So, and 1 bit here. So this means that we have 4 bits going in. So I'm going to need 16 locations in my ROM, 16 rows in my truth table, and in each row I'm going to have to provide 4 bits of output, right? Which is 3 bits of next state and 1 bit of unlock. Okay, and for now, we're just assuming that in is nice. We're changing the clock only after in has become stable. We'll get to fixing that simplification pretty much next lecture, but for now, that's what we're assuming. Okay, so remember that this output can either be a function only of the current state or of the current state plus the inputs. Almost all the machines that we'll explore are the so-called Moore machines, where the output bit is strictly a function of the current state. If we think about, which is called a Moore machine, if we think about how the signaling works and the timing, well, the important edge of the clock is the rising clock edge. So instead of drawing a square wave, I've actually just drawn up arrows to indicate when the clock goes high, because that's when the state register basically changes its value. And you can see that here. Shortly after the rising edge of the clock, a new state is available on the S state wires, and they come out. They then go through the ROM, and one of the jobs of the ROM is to compute this next state. And that has to happen with enough setup time, so before the next rising edge of the clock, the next state has been stable for the setup time of the register before the rising edge of the clock happens. And then at the next clock edge, that new state becomes the current state. So this notion of you're in a current state, you're computing a new state, at the next clock edge you transition to that new state. So there's this sequence of states that you're going through, which corresponds to making the elevator service the right person on the floor, or transmitting a convolutional code from the Cassini spacecraft back to JPL. I mean, pretty much anything in life that's sort of quote interesting involves a certain amount of having to sequence through a set of operations. Your computer, of course, is a giant sequential machine, And in fact, the sequence of states that it goes through is a sequence that we program, and we're going to be talking about programmable state machines in the lectures to come. So we're sort of on the stepping stones bringing us to a true programmable computer. Okay. Now, if you have a megahertz clock and you're putting your fat finger on the button, you're not going to be able to, you're going to sit there with your finger on the button for what might be many clock edges. And one of the things that we can do is we can adjust our state machine so that, in fact, when you press the button, you go into a particular state. And it's when you release it, when the machine finally detects on a particular clock edge when you've released it, that's when you make the transition. So rather than holding it down and saying, oh my God, the guy has just entered 7.2 million zeros, right? Because he held the finger down for 7 seconds on the button. What we're going to do instead is process. We're going to add some additional states to help us process the fact that when you push a button, first the contact closes and then it opens. And so we're going to account for that in our state machine. Now the little guy over here in the corner actually has identified a sticky wicket. I'm walking up to this combinational lock outside of one of the rooms in Stata, and I'm putting, right here in the 004 lab, and I put my finger on the button. It's not like I've suddenly looked over to see what the clock image is on the wall and said, wait, I have to wait just to the right moment so I don't violate the dynamic discipline. Right? I have no knowledge of the clock. So in general, processing information from the real world into these clock synchronous circuits raises the potential of violating our dynamic discipline, violating the setup and hold times for this register here. And that's a real problem and one that we'll devote a whole lecture to on Thursday. But for now, let's not worry about it. How many states are there in this state machine? Say, look, here's a picture, here's a hardware circuit that I claim is an FSM. Can you tell me something about how many states it has? Yes.
2 to the k.
It has at most 2 to the k. It might have fewer, but it has 2 to the k. Everybody happy with where 2 to the k came from? Those correspond to the 2 to the k combinations that I can get on the k state bits. A different encoding for each state that I'm in. Okay, suppose I put 2 state machines in sequence and I draw a big dotted line around that combo and say, that's a state machine. How many states does it have? Well, be brave. Make a wild guess. There's only so many things I can do with m and n. So
F times n.
m times n. Okay, and I think that's right because without any other information, each of these machines may independently be following its own sequence of states. And in fact, for every state that the first machine is in, I might be in any one of n of the states in the second machine. Now, it may be that I'll provide you more information that shows how the states are related, and now that may be much smaller. But in the absence of that, okay, here's a really interesting thing. Okay, here's an FSM. Can you discover its rules? If I put a box on the table that has some buttons and a light that goes on occasionally, can you show me the state transition diagram for what's inside? Okay, the consensus seems to be no. Okay, and that's wise of you, particularly if you've looked to the next slide. The answer is no. Okay, and the reason is you can never, without any bound on the number of states, you can't be sure whether you've explored all the behaviors that are hidden in the transition diagram. So you might press 0 and 1 and say here I'm going to press 0 for a while and nothing happens. I press 1, the light goes on. I keep pressing 1, the light stays on. I press 0, that's fine. And I press 2 1s and 3 1s. I'm pretty convinced that 1 turns it on and 0 turns it off. But what's inside the machine may, in fact, if you've pressed your 17th one, is when the light suddenly goes off again. So without any bound on the number of states, I cannot exhaustively enumerate all the possibilities because I don't know how long I need to keep going. Everybody with me on that? If you do have a bound on the state, and there's 2 to the k maximum states that you have, then you can go back and you can say, if I press 1 2 to the k times, okay, and then I wait and the light still stays on, I can say, okay, I think I'm pretty clear now that there isn't one of these gotchas at the end of one of these chains. So with the bound of the number of the states, you can do that. What about these 2 machines? They're clearly different. They have different arcs, different circles. I mean, one's a lot bigger than the other. Are they different? Okay, everybody's sort of shaking their head no. And what you're doing is you're looking beyond the superficial, arcs and arrows, and you're sort of saying, behaviorally, there's no way to distinguish them. No combination of zeros and ones will distinguish the diagram on the left from the diagram on the right. Right? So these are functionally equivalent, which means that if I had a choice of which one to build, I'd probably build this one because a 2-state machine will be cheaper in terms of the logic than that 5-state machine. Everybody happy with that? So there's this notion of equivalence. Okay, now for some fun. Let's build an ant. We all know how ants work. You see them sort of making this walk around and eating the rest of your lunch that you've thoughtfully left under your seat. But let's actually build a finite state machine that makes an ant get out of a maze. So here's a little maze. Our ants, for reasons that are lost in the mists of time, have 8 legs. For those of you who that doesn't strike you as funny, you should go look at an ant carefully. Okay. Okay, so the strategy of getting out of a maze, at least simple mazes, are put your right hand on the wall and just follow along, and eventually you'll come out of the maze. Okay, and so we're going to do that. We're going to build a little finite state machine for an ant that right antenna to the wall. So let's construct a state machine as we go. And follow along, because this is usually where you are in an engineering assignment involving state machines. You're saying to yourself, I forget the theme song for Lost in Space. There's actually been several Lost in Space shows, but anyway, I won't try to hum it. The idea is, here's an ant, and as an engineer, you sort of have to put yourself in the position of the ant and figure out what it is you need to do, and then you encode that in the states. So initially the ant is lost, and there really isn't much for the ant to do except to go forward until he hits something. So here I am, I'm the ant, I have a left antenna and a right antenna, and I can tell when one of them hits something. Okay, so it has 2 inputs, an L and an R input, and basically, in the absence of no other information, I'm just going to walk forward till I hit, hopefully, the edge of a maze, one of the walls in the maze. And that means that one or both of my antennae will suddenly signal a 1, saying I've done that. So I'm going to, basically, in the lost state, I move forward, so I can move forward, turn left, and turn right. That's what the ant can do. And if neither antenna is touching, I keep doing that. Otherwise, I've hit something, and now I'm going to change my behavior. So I'm going to need a new state to represent the fact that I found my first wall. So my strategy when I find a wall, so I'm going to come over here and walk up. My strategy, if I want to put my right antenna on the wall, is simply then to say rotate until my right antenna becomes clear. Okay, that's my first step. And what I'm trying to do, the behavior I'm trying to implement is going like this. I'm going to step forward, and I'm going to turn away from the wall and step forward, and then I'm going to turn back toward the wall, and my antenna will hit again. So I'm going to sort of be bouncing down the wall as I move forward. Okay, so here I've got in a situation where some antennas hit the wall. I'm going to rotate until both antennas are free. I'm going to rotate counterclockwise, which should have just made my right antenna clear the wall that I hit. Okay, that's what that state does. And now in the next situation, I'm now in theory parallel to the wall with the wall to my right. Now the next step is I'm going to step forward and go like that. So the idea is I'm going to keep sort of bumping up and down the wall where I'm sort of moving forward and I'm turning to the right and the left as I go like this. That's the behavior I'm trying to create. Everybody sort of with me on that? What happens if I'm bumping down this wall here, boom, 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 and I reach out, it's gone. What did I experience? A corner, right? And so what behavior do I want to do at that point? If you were the ant, what would you do? You're just going to keep sort of staggering around to the right, okay, hoping that you'll get around to the opposite corner. And so what we're going to do is that's represented by that diagram there. So that's a state diagram where the ant is basically running forward and hitting a wall, and away we go. Okay, is this the best we can do? In particular, did you notice the similarity between traveling down a wall and then processing a corner? Okay, so it turns out that this 5-state machine actually contains some equivalent states. So we look at this machine. 2 states are equivalent if they have identical outputs. In other words, I'm telling the ant to do the same thing in the current state. Are there states in this diagram where we're giving the ant the same control signal? Well, let's see. That one's only F. There's no other state that's only F. This one's TL. There's no other state that's only TL. This one's TLF. There's no other state that's both turning left and going forward. But these 2 states down here, turn right and move forward, these are 2 states in which the state machine is producing the same output. So those 2 states are potentially equivalent. Okay, and then considering these 2 states as possible candidates to be equivalent, I'm going to ask the question, does every input take them to an equivalent state? In other words, what I want to do is the behavior when I see an R or an L in this state the same as the behavior I see in an R and an L in that state? And in fact, if you look closely at the diagram, you will discover that in both cases, R takes them to wall 2, and not R, well, if these 2 states are equivalent, it's like a loop back to itself. Okay, so this arc and that arc are in fact arriving at the same state if those 2 states are equivalent, and so forth and so on. Everybody sort of happy with that? So it turns out that these 2 states are exactly equivalent, and I can replace that diagram with this diagram. Okay, why do I prefer this diagram? I know it's smaller, but practically, if you were going to run off and build hardware, what would be the difference? Yes, sir?
You only need 2 bits.
Right, going from 5 states, which required 3 bits, I now only have 4 states, and I only have to buy 2 bits. I only need 2 bits of state, which means my ROM is half the size. Right, I've taken one of the inputs away from the ROM, so I've reduced the number of inputs to the ROM by 1, which means that the total number of locations in the ROM has been halved. Okay, so I can go off and convert this diagram into a truth table. In some cases, I've used don't cares to encode the truth table. That'll make my logic simpler. And when I'm all done with that, I can turn that truth table into a schematic diagram. So let's have just a little fun, because what's life without a little fun? An ant. Okay, here's the truth table for the ant. So the yellow line shows me the current line. In other words, the ant starts off in the lost state, and see, none of his antennas are touching. So in fact, he has 0, 0. And so the yellow line will sort of tell me what the ant is thinking about in each step. Now that both antennae are on, it's going to rotate, whoops, it's going to rotate sorry. There he goes. Oh, now he's going to do that walking behavior. Here he's processing the corner. There he goes. Okay. This is actually a surprisingly sophisticated set of behaviors for what turns out to be a 4-state machine with 2 inputs and 3 outputs, right? I mean, this is, and in fact, a lot of the really, interesting behavior that you see in life, you sort of might speculate, could I build a finite state machine that implements that behavior? More on that thought in just a second. Let me go back to this. Anyway, you can, if you load up 6004, there's an ant.jar. You can run that and sort of watch him do his job. Okay. How do we initialize the state machine? How do we get the state how do we get the state machine hardware so that the encoding in the registers is in fact correspond to the initial state? Well, maybe I have to include some reset hardware. If my initial state has the encoding 0, often a convenient thing to do, maybe I'll include some reset hardware that forces that to 0. What happens if I don't use some of my state encodings? Well, we have to sort of defend against if we actually, cosmic rays hit and the state machine finds itself in an unused state encoding. We probably need to include some transitions that put it back into the world that we know. Okay. Okay. There's different ways. This is what's called a one-hot encoding, which involves, this is for the combination lock, where instead of having, encoding the state as an encoded binary number, we simply have one register for each possible state. That often makes the logic much simpler. Okay. This last bit about synchronizing input changes is something that we're going to deal with next time. But think about FSMs, okay? It turns out that there's a lot of behaviors in the world that are described by an FSM. It might be that if we dig down enough through all of our layers of particles and subatomic particles and sub-subatomic particles, maybe all of physics is really just a finite state machine with a couple of interesting transition rules. And here's the one I like to think about. Suppose you replace that read-only memory with a memory that can be modified, sort of to give your FSM learning behavior. And maybe that's all we've been all these millions of years, is an FSM with learning behavior. So a new philosophy of life, and you can think about that as you prepare for your quiz.